Japan is often described as the safest country in the world when it comes to earthquakes. Its cities are filled with flexible skyscrapers. Hospitals sit on base isolation systems. Buildings are designed to move, not to break. And yet, after major earthquakes, we still see damaged buildings. We see hospitals that cannot operate. We see infrastructure that stops working. So this raises an important question. If Japan has some of the most advanced earthquake-resistant designs on Earth, why do these systems still sometimes fail? This video is not about blame. It is not about disasters. It is about engineering reality, the limits of design, and what Japan teaches us about how failure really works. Japan sits at the intersection of multiple tectonic plates. Earthquakes are not rare here, they are a regular part of life. Over the last century, Japan has experienced some of the most powerful earthquakes ever recorded. Each one left behind damage. But more importantly, each one left behind data. Japan chose a different path from many other countries. Instead of trying to avoid earthquakes, Japan chose to engineer for survival. That decision shaped modern earthquake engineering around the world. But leadership does not mean immunity. Many people believe earthquake-resistant buildings are designed to remain undamaged. That is not true. Earthquake-resistant design does not aim for zero damage. It aims to prevent collapse. It aims to protect human life. It aims to give people time to escape. Engineers accept that damage will happen. What matters is how that damage happens. Buildings are designed to bend, to absorb energy, to deform in controlled ways. Cracks are expected. Movement is expected. Collapse is not. This philosophy is written directly into Japan's seismic building codes. In simple terms, earthquake-resistant does not mean earthquake-proof. Every engineering design is based on assumptions. Seismic codes define a design earthquake. This is an estimated level of shaking based on probability. But earthquakes do not follow averages. Some last longer than expected. Some release energy in unexpected patterns. Some exceed historical predictions. When that happens, buildings experience forces they were never meant to handle. This does not mean the design failed. It means the event exceeded the design envelope. Engineering manages risk. It does not eliminate it. After major earthquakes in Japan, many buildings remain standing, but they are still unusable. Why? Because non-structural systems fail. Ceilings collapse, pipes rupture, electrical systems shut down, medical equipment shifts or breaks. Structurally, the building survives. Functionally, it fails. Hospitals are a clear example. After the 2011 earthquake, many hospitals were structurally safe, but they could not operate. Earthquake-resistant design protected lives. It did not guarantee functionality. This distinction matters. A building does not stand on engineering alone. It stands on soil. And soil can fail. Many Japanese cities are built on soft ground or reclaimed land. During strong shaking, saturated soils can lose strength. This is called liquefaction. When liquefaction occurs, the ground behaves like a liquid. Foundations sink, buildings tilt, pipes break underground. In 2011, many well-designed buildings suffered damage because the ground failed first. No structure can outperform the soil beneath it. Design alone is not enough. Earthquake resistance depends on details. Reinforcement placement, connection strength, construction accuracy. Small mistakes can create weak points. Under seismic stress, those weak points fail first. Post-earthquake investigations repeatedly show this pattern. The concept was correct. The execution was not. This is why inspections, supervision, and quality control are critical. Earthquake engineering is not just theory, it is practice. Not all buildings in Japan were designed under modern seismic standards. Older structures reflect older assumptions. Before major code revisions, many buildings lacked proper ductile detailing. They were strong, but not flexible. Japan has invested heavily in retrofitting, but retrofitting takes time. As a result, failures often occur in legacy buildings, not in modern ones. Failure patterns are often historical, not contemporary. Buildings do not operate alone. They depend on electricity, water, transportation, communication. During major earthquakes, these systems can fail together. Even if a building survives, a city may not function. This is called cascading failure. Earthquake resilience is not just structural, it is systemic. To the public, failure means collapse. To engineers, failure is more complex. A building that cracks, leans slightly, and requires repair may have performed exactly as intended. Its job was to protect life, and it did. Understanding this difference is essential. Earthquake engineering is about survival, not perfection. Japan's experience changed global engineering. It taught us to focus on soil behavior, protect non-structural systems, retrofit older buildings, design cities as systems, not objects. Failures are not shameful in engineering, they are information. Each earthquake improves the next generation of design. Earthquake-resistant design sometimes fails because earthquakes are complex and uncertainty cannot be eliminated. Japan does not design buildings to defeat earthquakes. It designs them to negotiate with nature. And in that negotiation, saving lives is the ultimate success.